I'm Austin Percle. I'm the reporter for Group 3, and today I'll be talking about the results of the thermocouple experiment. Before I really get into the results, I want to talk about a few points of theory. I think if we go through a few things, it'll make it a lot easier to understand the results as we go through. So the first thing really you have to think about is in heat transfer, the rate of heat transfer is determined by the temperature difference. So if you have a specimen, in this case a thermocouple, that you put into a fluid, it's at a different temperature. Initially, the heat transfer is going to be very large, and you get a big change in temperature over the first couple seconds. And then as time goes on, the rate of heat transfer becomes less and less. And this isn't a linear occurrence, it's an exponential one. So if we want to kind of try to classify the time, the response with respect to time, we have to use this exponential, and the only real factor in there is the time constant tau. Tau is basically density and value and capacitance over the convection coefficient and the area. For a thermocouple, you can change the time constant by different geometries or materials, but mostly in this experiment, it's because we use the same thermocouple, it mostly has to do with the changes in H, which I'll kind of talk about later. But lastly, if you want to try to determine tau, what you're basically going to do is make time dependent upon the natural logarithm of this normalized temperature, or I'll call it temperature distribution. If you do that, then you'll see that you get a linear approximation, the slope of which we can take to be tau. And we can use the length of capacitance because if we assume that heat transfer from conduction is equal to heat transfer from convection, then we can basically assume the same temperature difference, and our capacitance is basically this ratio of the factors that affect each mode of heat transfer. So that ratio is basically where we get our tau. So now, getting to graphical analysis, I have it in this order, starting with hot. I'm basically going to talk about, show everything with the hot water insertion and removal, and then basically use the cold water experiment to back it up. So this is basically just the raw data, and you can see exactly as I described. Initially, you have a very steep rise, very large change in temperature, and then it just kind of planes off. Basically exactly what we would expect from this. Using the normalized temperature distribution, you can see that, and have the curve fit in an exponential here. It's not a exactly good curve fit, but I'll kind of talk about that in a second. But basically this just shows that your max value of temperature distribution is 1, and then it goes off as that ratio of as the temperatures basically converge to one another. And then we have this kind of a weird graph, but it's time versus the natural log. Like I kind of said earlier, if you make time dependent upon the natural logarithm of the temperature distribution, you'll get kind of a linear approximation, and that slope is where we get our tau, which I have later in the results, the tau from each experiment. This is the removal process. This is, again, the raw data. You can see here we have a inconsistency. This is mostly because it was removed from the ice bath and probably waved around just a little bit and wiped off. And then from there we get a mostly smooth line. Also, you can notice that it takes a lot longer. The insertion reached the desired temperature in about 6.7 seconds. This is upwards of 400, almost 450. So it takes a lot longer when it's removed, and that's because the different, air has different properties. Heat is transferred a lot faster through water, and that goes back to our formula where it depends upon this H. So we'll go to the normalized temperature distribution. Here we have a much better curve fit with the exponential. That's basically because for insertion, the heat transfer happens so quickly, whereas for removal, heat transfer happens over a much longer period of time. So any kind of small disturbances have a lot less of an effect on the heat transfer. Kind of hurrying along, again, we have a nicer linear fit to the graph, and that's where we get the tab from. And basically, like I said, I'll just show that everything in the cold water corroborates this. Again, the approximation for the insertion is not as good, but the removal tends to be a lot better. And again, that's where we get our tab from. So these are the results I got. Given that it was done on just one run for each, I didn't include any sort of deviations or errors because we only had one run to go off of, so no average values. You can't notice though that it's always it's consistently higher for removal, and like I explained before, it takes longer for it to happen, for the heat transfer to happen for removal. Also, you can see that for boiling, the hot water experiment, the values were the extreme set, and that's because there's a greater temperature difference between the room temperature and boiling water versus the room temperature to the cold. Finally, just to wrap up, if we're talking about thermocouples, it's kind of practically impossible to have one that instantaneously will detect changes in temperature. So we would rather design one where we know the time constant and we know basically how it behaves. The type K one that was used here is one of the less expensive ones, but for our purposes, it's basically adequate. That's my presentation. Thank you. Any questions?